And we're back in better than ever, still in 18-2, where we're dealing with reversible reactions and equilibrium. In the last podcast, we introduced the idea of the fact that reactions do go in both directions, both the forward and the reverse reaction. And a dynamic equilibrium occurs when the forward reaction and the reverse reaction rates are the same, where you can't tell that there's an overall change. In fact, there is no overall change in the molecules. However, if you watch individual particles, they will be changing back and forth between reactants and products. It's just that they're both happening at the same time, so from a distance, from the macroscopic level, we cannot see anything actually happening. And so if we go ahead and scroll down here, we've talked about Le Chatelier's principle. We will be going over these two examples, the cobalt chloride and the NO2 example in class. What we want to do now is try to quantify how far reactions move to the right or to the left. One of the last things that we discussed, or actually in the middle of the last section, we introduced you to the idea that reactions will either lie far to the right or they can lie far to the left. Well, we can quantify how far to the right or how far to the left they go, and you use what's called an equilibrium constant. So let me go ahead and get my pen. We'll go ahead and change back to our blue color. So if you have a reaction where A and B go to C and D and they are in equilibrium with one another, notice now I'm using a double-headed arrow. Sometimes we'll write it with an arrow going like that and like that, rather than the double-headed arrow, or a single line with two arrowheads on either way. You draw two lines with one half arrowhead going in one direction, one half arrowhead going in the other direction. Now, the equilibrium position will be quantified using the law of mass action. We are not going to derive the law of mass action. We're simply going to tell you what it is. KEQ is going to be our equilibrium constant, and that will equal each product. So we have the concentration of C raised to its coefficient's power. So you have a lowercase c here. Notice you have, here's the molecule, that's the coefficient, so therefore here's the molecule, and the lowercase c, the exponent, is the coefficient. We're going to multiply that by the concentration of D raised to its coefficient's power, lowercase d, and all that will be over the reactants, doing the same thing. A raised to its coefficient's power, and B raised to its coefficient's power. Now, unlike kinetics, where these exponents must be determined experimentally, they do not necessarily correspond to the coefficients. When you're dealing with equilibrium, it does. From the balanced equations, you can write the law of mass action, and this is what it looks like. And so that equation you're going to be able to have written down on the back of your periodic table, and you will be able to use it on the tests and on the quizzes. Now let's talk about what this means. If KEQ, our equilibrium constant, and by the way, that KEQ is called the equilibrium constant, if that is greater than 1, well, let's start with less than 1. If KEQ is less than 1, what does that mean? Well, it must mean that the denominator is larger than the numerator. And if the denominator is larger, that means that you have more reactants and fewer products. So that means that the reaction lies to the left. Meaning it is reactant favored. Reactant favored. Now the opposite, if you have KEQ that is greater than 1, that must mean that the numerator is larger than the denominator. And if the numerator is larger, that means that the products are favored, so that the reaction lies to the right. Or once again, product favored. Alright, so let's go ahead and practice this a little bit. Moving on down. Example number 1 says, write the equilibrium expression for the following reaction, where you have sulfur dioxide reacting with oxygen to form sulfur trioxide, and of course you have an equilibrium established here. So therefore, KEQ is going to equal products over reactants raised to their coefficients power. So the product is SO3, and it's raised to its coefficients power, which is a 2, divided by each reactant raised to its coefficients power. So you have the SO2 squared times the oxygen raised to the first power, but of course you just leave that off, and there you go. That is the equilibrium expression for that particular equilibrium. All right. Now, if you want to, go ahead and pause this podcast and work on example number 2 and example number 3, and then we can go over it together. Okay, so now we're back. Let's go ahead and take a look at this example number 2, where you have nitrogen reacting with hydrogen to form ammonia. Let's go ahead and color code this just to make sure everybody's seeing where we're going with this. We'll do the nitrogen in blue, we'll do the hydrogen in say a green, and then we'll keep the ammonia in the red there. Alright, so KEQ is going to equal the products raised to their coefficients power divided by the reactants raised to their coefficients power. Well, there is only one product in this case. Is the ammonia, the NH3, and that's going to be squared, and that's going to be divided by each reactant raised to their coefficients power. So that's the nitrogen raised to the first power, but of course you leave that off, and then the hydrogen concentration raised to its coefficients power, so it's going to be a 3. So there you go. There's the law of mass action, or the equilibrium expression for that particular equation. And finally, I think everybody gets the gist here, so we'll just stay with one color. We have KEQ is going to equal, well, in this reaction you have ammonia reacting with oxygen to form nitrogen dioxide and water. So it's going to be products over reactants. So we have the NO2 raised to the 4th power times the water raised to the 6th power over the ammonia raised to the 4th power and the oxygen raised to the 7th power. Alright, so there you go. That's how you write out the laws of mass action, or the equilibrium expressions for various equations. In the next podcast, we're going to start taking a look at how we can use this equation to either find KEQ or to determine an unknown concentration. We'll see you next time.